OK, so let's do one final example. The final example I want to talk about is Drell-Yan, which we almost kind of talked about already, but I'd like to talk about it in a little different context. So we talked about pp to xh, Higgs boson. Classic Drell-Yan is pp to xl plus l minus, but kinematically that doesn't really make too much difference from having a Higgs boson here. So I will talk about this in a little more detail than I did the Higgs example, and we'll go through some of the kinematics in a little more detail. So the reason that I want to talk about this process is there's kind of one function that we haven't yet seen that will show up in our discussion here. One kind of function that's ubiquitous and shows up in all sorts of factorization theorems, and we haven't seen it yet. So what are the kinematics? We have some momentum. Let me do it this way. Let me write it below this guy. So PA for the proton, PB for the other proton equals P for the X plus Q for the L plus L minus pair. So what are the important variables? Well, there's the center of mass, energy of the collision. That's just S in Mandelstam variables, but I'll call it ECM. So we remember what it is. PA plus PB all squared, that's the collision energy. That's 8 TeV, the LHC, soon to be higher. There's Q squared, and that's the scale of the hard collision. So the hard collision scale is not the center of mass energy. You take a parton out of each proton, and those collide, and they carry a fraction of that energy. You can see how much you have by looking at how hard the leptons are, and that's Q squared. It's useful to talk about a dimensionless variable, which is tau, and that's the ratio of these two variables, which is always less than or equal to 1. And then you can talk about the rapidity of the leptons, and you can write that in a kind of Lorentz invariant looking way by having a pb.q and a pa.q, so using capitals. So this is like this variable is like the theta for the leptons. So theta q. So again, it's just like our Higgs example, but let me draw it in a little different way. You can think about doing everything in the CM frame. Protons are coming in back to back. So then you have collinear particles because your protons are very energetic. So if this is a quark and this is an antiquark, you produce a virtual photon, and the virtual photon produces a lepton pair. So here's an n-collinear quark and an n-bar collinear antiquark. So the antiquark is coming in that way, quark is coming in that way. They annihilate, produce a virtual photon. That produces a lepton pair. That's Drell-Yan. OK, so in the CM frame, we're going to have Cn modes, Cn bar modes for the protons. And the antiproton. Some other variables that are useful to talk about are something that people call XA and XB, which are the Bjorken variables. And they already showed up in our previous example, but let me just define them. So these are taking tau and taking the square root of it and then splitting up the rapidity, e to the y and e to the minus y. And these are like analogs of the Bjorken variable for this problem. And it's actually these combinations that are showing up here. So if you put in what tau is, that's explaining what these arguments were. They're just the XA and XB. And kinematics, you can work out that tau is less than or equal to XA or B, and that they're less than or equal to 1. So there's some simple bounds on them. And then finally, you can work out that px squared, if you square it, is less than or equal to ECM squared, 1 minus square root of tau, all squared. And one more thing that you have are sort of the parton distribution fractions. So parton distribution variables, and they're bounded just like DIS. So XA and XB are things that are, if you like, leptonic. You might call them that, but they're things that are external to the QCD, right? They're just measuring properties of the leptons, Q squared, the center of mass of the collision, and Y, which is a Y of the leptons too. So everything here is not a QCD variable. And then there's these QCD variables, CA and CB, which are inside the parton distributions, and they're bounded. Just like we had a bound in DIS, x less than or equal to c less than or equal to 1, here we have two analogs of that formula.
So the rapidity is the rapidity of the sum of the pair?
Yeah, that's right. The rapidity of the Q. So really this is like, this is my kind of, this is like log of, the thing that's important here is the log of Q plus over Q minus. It's the rapidity of the Q. Basically. Yeah, you could talk about measuring individual things about the leptons, but then you would just be tacking on something onto the Q and taking something else out of it. All right, so what kind of, so this is just some kinematics. What kind of limits do we want to think about? So we already talked about one example where we would measure Q perp. That's what we were doing in the Higgs case. And I'm not going to talk about that case. I'll talk about 3 other cases. So if we didn't measure Q perp, then there's kind of 3 different things we could do that I'll talk about. Let's see. Organize my board better. I'll tell you about the kinematics of each one of these, and then I'll draw a little picture for each one. So in the inclusive process, this is the analog of what we did for deep inelastic scattering. So deep elastic scattering, we said the Bjorken X variables of order 1. Here we could say that, in some sense, tau is of order 1, as well as XA and XB are of order 1. And in this case, what you're saying about px squared is that it's hard. It's of order q squared, and if tau is of order 1, then that's of order ECM squared. So these things are all hard variables. And in this case, the way you should think about what's happening in the process is the following picture. So you have your partons coming in, or your protons coming in, and basically you're allowing radiation that's hard anywhere. So hard is supposed to be pink. You're not constraining the radiation. You're really allowing hard radiation. So hard. Your X is hard, and you allow jets in any direction, for example. And then somewhere there's a lepton pair. You can pick purple. But it's not constrained either. It's really fairly general. My picture's too big. I'm going to run out of room. Oh well. We'll do this. So I want to draw analogous pictures for the other cases. So in the endpoint, you're taking a different limit. What you're doing is you're taking this tau goes to 1. And you can see from over here that if tau goes to 1, that forces XA and XB to go to 1. And if XA and XB go to 1, that forces CA and CB to go to 1. So you're really talking about probing the proton in a very special kinematics where everything is going to 1, and you're basically, in the hard collision, you're forcing all of the energy to go into the parton that's colliding. So the proton, the full proton momentum goes into the active parton. just say it that way, active parton. So that changes the picture because it also, if you look at it, so when tau goes to 1, it says the outgoing energy, the full ECM squared, is going into Q squared, which is the leptonic variable. So all the energy is coming in on the partons and going out on the leptons. So you don't have hard radiation like this anymore. The only thing that you could possibly have is soft radiation. So in this case, what happens is this picture, just make my lepton a little shorter, changes. You still, of course, have these incoming guys, but what happens is that everything outgoing is soft. So green. You have soft radiation. Like that, and then it turns out also that in this case, the leptons end up having to be back-to-back. Because you can't have any transverse momentum. That would be, there's nothing for the transverse momentum to recoil against. So that's a possibility. And then there's a third thing that we'll talk about, which is what I call isolated. And it, in some sense, is trying to combine these two pictures here without taking a limit on tau. So you might say, well, what's the most typical event at the LHC? What is the kind of where is most of the cross-section for this process? And that would be in a situation where tau is not in the endpoint. It doesn't go to 1. It's kind of an order 1 quantity, actually. You typically get XAs and XBs that are like 0.1 or 0.01, small x's. Depends on what Q squared you look at, but the typical ones you're interested in are small x's. So you don't want x to go to 1, so tau can be of order 1. But if you ask what the most probable thing for the px to do, if you have these collinear particles coming in and they start radiating, well, they like to radiate collinear particles. So the most likely thing that will happen is that you'll get collinear radiation from the incoming particles. And you can look at that by studying the following situation, where you constrain px squared to be 2 ISR jets. So the picture, we'll talk about how we do that in a minute, or one way of doing it. So the picture would then be as follows. We have these incoming guys, which now I'm going to try to draw some radiation for. So pick some colors. So here's a collinear guy in one direction. Here's a collinear guy in the other direction. And they can radiate. They radiate prior to the hard collision here, so you're getting some jets from these guys that look like this, and then from this guy, the symmetric thing, like that. And then in the central part of the collision, you just allow soft radiation. So this is the isolated scenario. And if I draw the leptons, it turns out they don't have to be back-to-back, but there is some constraint on their kinematics. Basically, they're back-to-back in the transverse plane, but not longitudinally. But we won't dwell on that. OK, so this is a sort of third kinematic configuration. So even though we're interested in one process, we've already just described to you 4 different ways that you could think about looking at it. And those 4 different ways will lead to 4 different factorization theorems, because it's a different kinematic setup. The first one was PT of the Higgs. That led to this rapidity divergent type factorization theorem. Inclusive, we'll talk about in a minute what it looks like. Endpoint and isolated, they all will have different formulas for the factorization theorem, and that's because they look different. I really should say that this is ultra soft, not soft. And so this is ultra soft 2 here. It's ultra soft. This is some CN radiation, and this is CN bar. All right. So we'll see how far we get. OK, so let's start with inclusive. So the x is hard, and so the way you can think about it is that what you're doing is that you can use kind of an optical theorem type picture where you're cutting these forward graphs. These are the leptons here, which are the things in the final state. It's the virtual photon, and I'm squaring it, and in comes QQ bar, and then squaring it, so QQ bar on that side as well. And then if you think about it, every kind of radiation gluon that I would put across this cut, I can think of as kind of hard. And so I can integrate it out. And so what you're going to get is, if you just think about this process, when you match the cross-section, you're going to get some 4-quark operator in SCT. So this will match onto an operator, which is a 4-quark operator, where 2 of the quarks are n-collinear, draw it like this, and 2 of them are n bar. Okay, because that's the external particles. We have Qn, Q bar, and bar. So we're going to get that. And that, we know how to write down the lowest order operator for that. That's just going to be chi bar chi, chi bar chi. So we have a 4-quark operator in scat. Which you can write after doing a Fierz in the spin with all the n-collinear fields together. You can work out constraints on Dirac structure. There's only one operator, basically. It's not quite true. So you could have a gluon operator, an operator with 4 gluon fields. That's the analog of this one. Then you would have to have some higher order diagram in order to take those gluons and attach a photon. There'd have to be a quark loop inside the hard function, but you could also have a gluon operator with 4 B's. So let me just say there's also Bn, Bn, Bn bar, Bn bar. So you don't have a color octet structure, no TA, TA. And again, that's like our B to D pi example, where if you had that structure, it would vanish when you take matrix elements. So there's no TA, TA. There's constraints on the color contractions. Here, there'd have to be, these guys would have to be contracted. Those guys would have to be contracted. You can make the field redefinition. The field redefinition, the Y's would cancel out. So there's no ultrasofts here. Leading order. And if you take these matrix elements of these objects, you can kind of guess what they're going to give. This is just giving a PDF. Each of these are giving a PDF. And they're the regular PDFs, the standard ones. Because we didn't measure a perp momentum, we just get standard PDFs. So some parton inside the proton, which would be a gluon from these guys, gluon PDFs, or quarks from these guys. And it depends on some x, some mu. X could be XA or X could be CA or CB. So let me just write CA. And that's really all you get. So you have a hard function and then 2 collinear parton distribution functions. So the cross-section in these limits that we talked about come from the kinematics. There's some hard function, which is an inclusive hard function. Like in DIS, it depends on the ratio of these variables, but now there's 2 of them. It depends on Q squared, depends on mu, and then there's times PDFs. There's an important caveat here, which is if you want to derive this result, you have to make sure that the degrees of freedom I've told you were the degrees of freedom are the right ones. So what did I tell you? I told you we have CN, CN bar, and ultrasoft, right? And that from the kinematics, it's a SCAT1 problem. Turns out there's one other type of degree of freedom that you could worry about, and that's called the Glauber gluon. And to derive this, we must know that that doesn't matter. What is a Glauber gluon? It's a Coulombic gluon between n and n bar particles. So it's a Coulombic type potential. It goes like 1 over pt vector squared. And that's a Glauber. It's called a Glauber exchange. So it's not an on-shell particle. It's like a potential. But you have to know that those actually are irrelevant in order to get to this formula. So there's a little more work involved, which I'm not going to talk about. OK, and that's going to be true, actually, of all the other cases that we do as well. So what about this threshold limit? How does the formula change? Well, you could think about how the formula changes is it's really a change of this h in the threshold limit. Because what's happening is that you're constraining the pink radiation and making it green. Let me go keep my pictures. So if we want to go from here to here for the threshold limit, then only certain terms, if you like, in the Hij are included. So if you wrote out that function, really what it corresponds to is that only the most singular terms in the variable 1 minus tau, in these 1 minus type variables, are included. So delta functions of 1 minus tau, plus functions of 1 minus tau, those are the terms that you would include from the H. Whereas the inclusive one has much more in it. This keeps only particular terms. But there's also different hierarchies of scales, because now 1 minus tau is small. And you want to, for example, sum logs of 1 minus tau in this situation. And that's what the factorization theorem in this threshold region does for you. So the Hij inclusive gets turned into the following. So this is the modification of the factorization theorem. So there's a soft function for that soft radiation. And then there's a different hard function. Which is only a function of q squared. And it's like the square, this guy here is the square of a Wilson coefficient again. And I and j are just pairs of quarks, UU bar, DD bar. There's actually no gluons in this case. So the terms with the gluon PDFs actually get suppressed. They're not singular in 1 minus tau. And we get this formula here. And now there's going to be some running that you have to do between the hard scale and the soft scale. And that running is going to sum up these logarithms of 1 minus tau. OK? So I'm not going to go through that in any more detail. I'll spend a little more time on this one. So what about isolated Brillouin? This one is a little bit different than the other ones, because we have to measure something about the process to know that it looks like this. If we really want to drive a factorization theorem, here we were measuring tau. But now I'm telling you I don't want to measure tau, yet I still want to distinguish. So I don't want to measure tau. I don't want to constrain it to be close to 1. But I still want to distinguish between these two, right? And if I'm going to distinguish between those two situations, I need to measure something else. And we can do we could measure something that's exactly like what we did when we did E plus E minus to dye jets, because this is really like dye jets, but they're just initial state jets rather than final state jets. So that's what we're going to do. We only have 4 jets. We have tau that's generic, so the C's are not being forced to go to 1. And so we need something that we can observe to do that. And here's what we can do. Let's do something that's the analog of E plus E minus to dye jets, but in this, for these initial state jets. So we say that Px is a sum of momentum in 2 hemispheres. The hemispheres A and B are just the dividing line of the center of mass of the collision. So very simple, perpendicular to the beam axis. And then we just say that Ba plus, so this is just a 4 momentum decomposition, but we can look at Ba plus, which is like dotting the n vector for one axis into Ba, and that's a sum over particles in one of the hemispheres. And then likewise for B. So this is if I write it in terms of energies and rapidities, it looks like this. So this is some observable Ba plus, and then I can constrain that Ba plus, which is exactly like constraining the plus momentum in one of the hemispheres to be small. And what that does, if you constrain the plus momentum in this hemisphere to be small, it'll allow ultrasoft radiation, because they have small plus momentum, and it'll allow collinear radiation, because they have small plus momentum. So constraining Ba plus constrains all the plus momentum in that hemisphere, and that puts you in an SCT1 situation where we have a figure like that one. So rather than constraining the perp momentum, we constrain the plus, and then we get SCET1. So take Ba plus to be less than or something, which you could say, well, less than or equal to some cut, let's call it B cut, and that is much less than Q. And then we do the same thing for B plus, which we define as NB, which is NA bar. Okay, so the notation here is a little awkward, but we do the same thing here. Say this is less than or equal to some cut, and that's much less than Q. And by demanding small plus momentum in both hemispheres, appropriate momentum, the small components, these are the small components, that puts us in a SCET1 situation. So we have CN, CN bar, and ultrasoft, and those are the allowed types of radiation, and that's what I drew in my figure. So hopefully that's clear. All right. So what does the factorization look like in this case? Well, you have 2 types of things that are collinear, if you look at the figure. There's the initial state proton, right, which came in here, and it was collinear. So here's a proton. And then it's cruising along, and at some point, it widens out like this and becomes a jet. So this here is collinear at a smaller scale than this here. This is a jet, right? It's got large invariant mass relative to the proton mass. So there's actually 2 types of collinears, and if you really want to draw the mode picture for this, here's what it would look like. So here's our collinear hyperbola, Cn, Cn bar. We have an ultrasoft hyperbola. And then somewhere we have a lambda QCD hyperbola. And there's protons that sit on the lambda QCD. So this is like Pn bar, if you like, or give it a different name, Pn. And then there's hard modes. So what we'll do is we'll not really worry about distinguishing these. We'll think of them all together. So we'll just have SCT1, where we have ultrasofts here, a Cn and a Cn bar. But then we'll later have to worry about factoring the, this includes the jet. This is the linear jet. And this is the proton, right? So both objects will be in the same function at the beginning. And then we'll have to factor them later if we want to separate those scales. It's a similar trick to what we used before in another example. But it was for soft in that case. So if we just keep these guys together, then it's just a sket one. Just have these modes, go through the factorization, and this is what we get. So we can measure q squared, rapidity, and we can measure these two hemisphere momenta. The hard function is again the square of a Wilson coefficient. Just as it was in the threshold case. We get some collinear functions that are called beam functions. And they have an argument that's a plus times a minus momentum. So this WA is like a minus momentum. We have a Bjork and X variable, and we have mu. There's one of these for each direction. So there's one for the B direction too. And then there's a soft function. And it's a hemisphere soft function. It's really exactly analogous to the soft function that we had in E plus E minus the dijets, except that the Wilson lines are incoming instead of outgoing. So it depends on 2 plus momenta and mu. OK, so the factorization theorem involves these B's, which are called beam functions. So this is a beam function for parton I. And parton I could be a quark or a gluon in this case. Well, sorry, parton I here will be a quark, actually. In this case, quark or Q or Q bar. But you have analogous functions for gluons as well that would come in, for example, if you were doing Higgs production. So what is this beam function? It's the one object that we haven't seen an example of before. And it's really a matrix element of an operator that we've studied in many different situations. It's just the chi-bar-chi operator with different arguments than we've studied previously. So it's a slightly different matrix element of the chi-bar-chi operator. Because what we're measuring is both the large momentum and the small momentum of that operator. When we measured just the large momentum, that gave us the PDF. But now we're measuring also the small momentum, which you can write like this. So it's a proton matrix element of a chi-bar-chi operator, where if it was a PDF, this would be 0 and 0, and we just have the minus momentum. But now we're measuring, if you like, the other momentum, which is like a plus momentum. And I wrote it in Fourier space. So the plus momentum that you're measuring is here. Those are the two variables that are showing up on the right-hand side, as well as the minus momentum of the proton. So it's just a different matrix element than one we've had before. The jet function, remember, would be vacuum matrix element of chi-bar-chi. And the PDF, standard PDF, would be proton matrix element of chi-bar delta chi. And it's just really, the arguments are slightly different, and that allows this thing to contain both kind of a jet, initial state jet. In this case here, the jet function, you'd have some variable and 0. In this case here, you'd have 0 and 0. And so if you like, what this guy is just a combination of the two things we studied before. We studied the jet function, we studied the PDF. Now this has both inside it. And if we go through this final factorization between there and there, then that's like a sket 1 to sket 2 matching. And So we can integrate out the perturbative radiation, which is the jet function, right? That's perturbative. And this is non-perturbative. We can separate those by doing another matching, and that gives a factorization theorem for the B alone that looks like this. So there's some perturbative matching coefficients, which are called I. And then you get a standard PDF. So this I is the thing that has in it the jet radiation. This is sort of an I for the jet. And then this is the PDF. Okay, and the T scale here is large, and what you're basically expanding in is you're expanding in lambda QCD over T. So if you ask what am I doing to make that separation, I'm expanding in lambda QCD over T. There's no T here. The T is perturbative. It sets the scale for the jet. And this F is a non-perturbative distribution function. And that's then the full factorization theorem, putting those things together. So these beam functions are kind of, they are things that show up whenever you have a process where you ask for a particular number of jets. And if you asked, for example, for a particular, if you ask for if you ask for this setup plus one more jet, how would things change? Well, you'd have the same beam radiation, the same initial state radiation, and you'd add one more jet function to this formula. So that would be exclusive one jet production. Or you could have two jets, then you'd have two jet functions. In each case, you have a different soft function, but these beam functions are going to be always showing up because they're describing this initial state radiation. So anytime that's an allowed thing, then it'll show up. If you start doing perp measurements, then you might have perp-dependent beam functions. Okay? In the same way that we could get perp-dependent PDFs, in some sense, a perp-dependent PDF is like a beam function. So that's kind of the last function that you need to know about that is kind of a generic thing that shows up with these factorization theorems. And we're out of time. So we'll stop there. And that's it.